Dear friends and colleagues, thank you very much for being here today. We are resuming our series of seminars within the PhD program of Aerospace Engineering, and it is my pleasure to host today Nicolas Gauguin. Right, sorry for the pronunciation. He has a strong background on mathematics and applied mathematics and computer science. Indeed, he's a mathematician. He did his PhD at DLR and then joined DLR as a research scientist for a few years, applying mathematics to the aerospace field. And after that period, he jumped into the academia. He was first assistant professor at Berlin, Humboldt University, and then moved to Aachen. He was also at MIT, and finally he got a chair, the chair of the computer center at TU Kaiserslautern, where he's a full professor now. He's also, among other things and other merits, he's an associate fellow at the American Institute of Aeronautics and Astronautics. And he's going to be talking about gray box modeling with applications in data-driven turbulence modeling. I think it's nice to have this gray box term. It is not white nor black. And it's nice to see that data-driven are now somehow leveraging on gray things and not black things anymore. So thank you very much. The floor is yours.
Thank you. So this mic is on. Thanks for the kind introduction and for the invitation. It's a pleasure to stay here. So as mentioned, gray box modeling with applications in data-driven turbulence modeling. So why gray? So we have a white part and a black part which we are blending. So first principle simulations, this is the white box modeling, and the artificial intelligence part where we use machine learning is the black box part, and both sides can be linked, and then we get gray box modeling. In the first part of the lecture, you will see how we make use of white box models to parameterize for machine learning models. And in the second part, you will see that even when you apply in special applications black box models, you can make use by analogies to classical optimization methods in the training of machine learning. You can make use of white box models. In that sense, it's a gray world and not a black or white one. So for the data-driven part with field inversion, we do first a data assimilation. So you will see we have a Reynolds average Navier-Stokes solver augmented by a Spalart-Almaraz turbulence model, which is known not to be well adjusted to tackle separated flow. And we then do a trick here in the transport equation of Spalart-Almaraz in front of the production term. We smuggle in factor beta, which lives everywhere in your flow discretization, so everywhere on your grid. If beta is 1, that's the standard Spalart-Almaraz turbulence model, and if it is something around 1, then it's an adjustment by the production term. You could also do this with the destruction term, doesn't matter, or put parameters somewhere else. So the data assimilation part is, here we have two examples. We have tracking type functionals. We want to meet a prescribed known or measured pressure distribution, or integrate over the pressure distribution to get the lift, and then to meet the target lift. And you see here, that's the data assimilation part, so it's high dimensional. You may have millions of grid points, then you have millions of parameters, so beta is a field variable. And we want to minimize here these two functionals by adjusting beta. So you need, for derivative-based optimization schemes in this data assimilation and this inverse design problem, you need to compute gradients of the dimension of millions, and therefore we make use of adjoint methodologies. Okay, we have regularization terms here, lots of things, yeah. Okay, and once we have this data assimilation, we have for the points where we know physics, maybe by experiments. You will see we compare with experiments. We parameterize in the sense of this data assimilation for a field beta. And then for other easier features, like wall distance or vorticity, something which you can easily get in a computation, we learn how this is linked to this field data better. And then in the reconstruction field, after you have done via deep learning and machine learning algorithms, you learned this mapping from your feature queue to this beta coming from the data assimilation. You can do reconstruction. So that means you just start a simulation. Then out of the first simulation step, you get out the queue. Then you feed in the queue in your trained ML model that spits out an update in your beta. You put this in the transport equation, do the next step, and so on. Yeah, and hopefully then the result trained by the data coming via the data assimilation in your machine learning model gives you better results in the simulation. Okay, so, and that's the chain. Whatever here is in red, these are tools of open source communities like the SU2. It's a multi-physics package developed over order of 200 groups worldwide with roughly 1 million users, becomes more and more popular, especially in the United States. And my group belongs to the, say, core team of about 7 teams who do the overall framework, and I augmented with 3 of my tools developed in my group. The code differentiation package is an algorithmic differentiation package, CodiPack, and the parallelization packages for algorithmic differentiation to set up the adjoints automatically, also in a multidisciplinary sense. So that means you have a design suite here, an open source design suite, which is also easy to maintain by the machinery we provide with our AD tools. And then we do the field inversion. That's a standard optimization in our point of view. Then we hand over these beta and we do the learning process from the feature to the beta. And if it is trained, it is just used to spit out the forecast for the beta. And you will see there is also a link to other standard tools in the machine learning world, plus a specialty from the parallel in time community. There is a tool, XBraid. I will show you some analogies to simultaneous analysis and design in shape optimization for aerospace. And we do then on the second part this view on the black box machine learning model for residual deep neural networks, and identify this by being nothing but an optimization with ODE problem. And then we make use of these one-shot method, all-in-ones methods, and the use of the tool XBraid. But we do this now step by step. So these are again the tools here: SU2, CodiPack, MEDIPack, OptiLib. So our algorithmic differentiation tool is well tuned for high performance computing applications. So we really apply this here on this open source package. So everything you will see today has been done with SU2. However, we apply this also for really industrial solvers or solvers provided by German Aerospace Center. In that case, in Cologne, the DLR trace code is a turbo machinery code. It's really the production code of MTU aero engines for the design of turbines, and that we have also differentiated with my package CodiPack. So that is really capable to differentiate automatic through MPI and OpenMP directives, and that gives you then also the potential to scale on many core architectures where you blend MPI, OpenMP, accelerate parallelization environments for acceleration. Okay, so we start with the data assimilation first. So this is a standard setting. So we have a objective function for the optimization. The cost function is j, which we want to minimize. Phi is the parameter. Yeah, imagine this beta field, for example, highly dimensional, and a constraint is to be fulfilled, r equals 0. So this could be our Navier-Stokes equation, for example. And a standard way to set up the optimality conditions is you define a Lagrangian where you augment your scalar cost function via introducing a multiplier lambda multiplied by your state constraint r, which is 0. So this gives you a scalar 0. So whenever this PDE constraint is fulfilled, L equals J. Yeah? And then that's Lagrange formalism. Optimality criteria is nothing but a first order necessary condition for extremality optimality, so for stationary points. That means this function L depends on J and R, therefore it depends on W and phi, and in addition by the Lagrangian multiplier lambda. And then the necessary condition is that the total gradients, so the partials with respect to lambda, W and phi, vanish, so become 0. The first, the derivative with respect to lambda means r has to be 0. That means our constraint has to be fulfilled. If we differentiate with respect to the state variable, so our flow state, so to say, to be 0, so this is this partial of j with respect to w plus lambda transposed dr dw, which is a matrix, because this is a vector differentiated by a vector, gives a matrix equals 0. This is the adjoint state equation. That looks so unguilty. It's just a linear equation. If you transpose it, it's dr dw transpose times lambda equals minus dj dw. Looks easy. Yeah, so you have a nonlinear problem to solve in residual form. If this is fulfilled, then you solve this adjoint equation. And then if you flunge in here the lambda information, you get this partial here with just partials in j and r with respect to phi. And it turns out that the partial of L with respect to phi is nothing but the total derivative of j with respect to phi. So it's the gradient. And the cool thing is, for the cost of one flow simulation and one adjoint simulation, which pops out the lambda, you get by this design equation in one stroke many inputs in your gradient, the components of your gradient, so the total derivative of j with respect to phi. So that's the standard way. And what you see here, that looks like a finite dimensional scalar product in L2, Euclidean scalar product. Then these are the optimality conditions, yeah, and you could even do this optimality conditions to derive them in means of continuous equations. Then it's this continuous adjoint method. So that's the adjoint methodology. However, that's not really the truth, because the optimization problem usually doesn't live in this space L2. It's more complicated in continuous space. You have to hope that you have so-called Hilbert space settings. So that means that the norm in this space can be expressed by a scalar product. So scalar product, the root of it is the norm. So the norm is the squared of the scalar product. It's hard to know if we have Hilbert space setting. Usually this the nature of the simulation here lives in some Sobolev type space, and not each Sobolev space has really Hilbert space setting and so on. So you can do a trick, you derive everything in L2, and later on you translate it into a Hilbert space setting, the derivative information, which is close to the real world problem. Yeah, so that is something quite often is hidden from the continuous adjoint guys. They say we derive continuous adjoint equations, but then they do it in finite dimensional L2, which is kind of cheating because it's a more complex thing. But if you do it discrete or continuous, this is more or less done by most of the groups worldwide. I don't like it, and I explain you why I don't like it. It has practical reasons, and somehow it's cheating. So you say I fulfill perfectly the state equation, but when you guys solve Navier-Stokes or even easier problems, you know you never get an exact zero here. Yeah? So that means you have a residual of something, say 10 to the minus 6, then you are happy. But what does that mean then for the information of your adjoint here, if you do it really in this residual form? Yeah. So the linear system, the error in the lambda, doesn't depend on the errors on the right-hand side, if you put this on the right-hand side. It only depends on the condition number of this matrix, and you can do nothing against the condition number of the matrix. Yeah? So if you have a fluid flow problem with separation, usually the condition number of this matrix is by the order of 10 to the power 8. And that is the amplifier of the error you do here. Yeah, so that means if you solve here 10 to the minus 6 accurate, and you amplify it with 10 to the 8, your accuracy is 10 to the power 2. So that means not accurate at all. Yeah, so you make an error, or even worse, you don't get convergence. Yeah, it's a very stiff system then here. Yeah, and that is why I don't like it. And it is really not the discrete way, because the discrete way is here the green world. So next to gray, we have also green worlds here. You have an iterative process. So you have an iterative process to solve for this residual equation. So usually it is something like, say, a pseudo time stepping method or a Newton's method or a backward Euler something, which you can write in this fixed point form. And then by Banach's theorem, we know that the derivative of the iterator G with respect to W measured in a certain norm. Yeah, if you do this in the 2 norm, you can analyze the spectrum. And if the spectrum is strictly contractive, so all these eigenvalues are less than 1, this yields convergence. Okay, and that is what is behind. You don't solve a residual equation, you have an iterative process, and then later on, when you are lucky, then the difference between your G of W minus W, which is the residual, is 0. Yeah? But usually it's something in order of 0, say 10 to the minus 6. And if I replace the exact residual by this increment here, multiplied by the lambda, and then derive optimality conditions, it looks like this. And it turns out, yeah, it's equivalent. So if we have really the perfect fixed point, we have the perfect residual, then it's equivalent. But let's look what happens if we have still a defect here. So a residual of order of an error of, say, 10 to the minus 6. It turns out that here in the adjoint system, we have this equation. And I can put this lambda times identity on the right-hand side, and all the rubbish which is on the left-hand side left is an iterator in lambda, yeah, because I have lambda transpose times dg dw still in it. So I have an iterator in lambda, and that makes sense. For the forward problem, I have an iterator in the state, g, and in the reverse, in the adjoint, I have an iterator in the lambda, this n transpose w. We will see this is shifted Lagrangian notation. We will see in a minute what that means. Okay, and now the thing is, when I have a fixed point form for the forward solve, I yield a fixed point form for the reverse, the adjoint world. And the rest is more or less the same. Yeah, I have here the state equation, which says that fixed point has to be reached and so on. But what about this adjoint iterator? Before we had here the dr dw, which is heavily ill-posed. And the question is, what is now the contractivity of this adjoint system? And I tell you, that's very well posed. look, as we had here the derivative with respect to W and observe the spectrum, we have now from this guy the derivative with lambda, because we have to iterate in lambda and look at the spectrum of that. And that is just this here, these terms here. This doesn't depend on lambda, that doesn't depend on lambda, but it's factored with lambda. So the derivative of this with respect to lambda is exactly this term. So the derivative of the adjoint iterator with respect to lambda is just dg dw, which was the thing for the forward problem. And that was fulfilled. So that means if I derive optimality conditions that way, I inherit perfectly the contractivity. That means whenever the forward scheme was contractive, the adjoint scheme needs to be contractive. Yeah? When you now ask me why the hell the people don't do it that way, because it's numerically stable, it guarantees convergence, it doesn't amplify errors and so on, yeah, you shouldn't do anything else. So the truth is, it's hard to get this adjoint iterator, because to get the dg by dw, I apply algorithmic differentiation. The funny thing is, I apply algorithmic differentiation in reverse mode, so I use an adjoint operation to generate a driver program to compute the real adjoint information. And that means I have to differentiate through the whole solver and not only to flux residual routines. Yeah? So that means it costs you something, but in my case, it's done by my automatic differentiation tool. I don't have to derive everything. And yeah, so that's the first message. And when you have this setting that is so stable and avoiding additional errors, that it has the potential to be augmented to so-called one-shot methods. Yeah, that comes in a minute. Okay. Here you see how this is realized in the SU2 package. We differentiated it in that form, and you see here the density residual compared to the adjoint density residual for Spallard-Almaraz as well as Wilcox K omega SST, and you see the slope of convergence is really inherited. Yeah? And you see a memory increase of just a factor 7.2. That's due to the fact that our tool is nicely tuned for efficiency, and the wall clock time is just increased by 20%, which is also, when you have experience with algorithmic differentiation, something which is usually not allowed. Theoretically, it should be at least factor 2 or higher. That it is in our case so efficient has the reason in additional tricks from computer sciences. We make use of features of C++. We differentiate here by the way C++ code, and the AD tool uses operator overloading techniques, and we make use of expression templates. Okay. So that is the framework we have, and this framework we use to minimize now these two functionals, and the derivative is these functionals differentiated with respect to this beta. Yeah? So you differentiate your solver, which spits out these functionals with respect to these parameters, which are in the augmented transport model with the negative Spallard-Almaraz transport terms. Okay, and here you see how it works. We chose this case here together with our collaborator at German Aerospace Center. So we have this beta here everywhere in the field. It's here having this Reynolds number and Mach 0.1, but highly separated flow, high angle of attack of 16 degrees. And you see here in boxes the measurements. And then you have a green line, which is the fit with the CP values directly, and in blue, the fit with the integrated values lift, but compared to the CP values. And you see here in red, the initial Spallard-Almaraz is not yielding the true solution, but by augmenting all the data and doing the data assimilation, so this adjoint-based optimization with the beta parameter in the field, you see we can perfectly meet the pressure distribution. And the next message is on the right-hand side, you have the friction coefficient, and then you see if you have this local varying CP degree of freedom, you get non-physical friction behavior, and that says, okay, reducing separation has to do something with lift, and the integration over CP has a smoothing effect, blah, 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 blah. So you see also, you should have physics in mind to choose the correct cost function. Yeah? So here, both are somehow mathematically equivalent, but the side message here is, never use this functional, please use that functional, then you have a good friction behavior, and you can meet this here. Okay, and now we have the beta field, and that we hand over to our machine learning. So the features we have is dimensionless wall distance, pressure, and velocity gradients and vorticity, and that we want to learn the link of this feature, which is then having the abstract variable name Q linked to the beta. Yeah? And then we do this with an additional trick. So we view this to be a picture, yeah, to be independent of mesh resolution and geometrical scaling or shape definition. So we map here these values on an image. So that means we map the features Q on standard pixels in the image Z. So that gives us flexibility to incorporate further data, further cases, different resolution. And on the top, it has a feature in the sense of regularization of the machine learning problem. Yeah? So the technique behind here for people who work with machine learning, it's just encoder-decoder technique. And then you see here we meet the losses. So the output is here, this is just one section of the mesh. We have millions of outputs, beta, so this is one point in the output layer. And we map from the Z's to the beta for all the betas. It's a big array of nets, and here we have the compression and decompression on top. Yeah? And then we do here the optimization of the loss function. And you see this is exactly mathematically the same. This also in verse design data assimilation. And we also do a regularization here, Tychonoff regularization. Okay. Let's see how it works. We have here NACA case, 0012 and 0021. On the left-hand side, you see in red experiment and in blue simulations with the standard Spalart-Almaraz, and that we hand over to the training. Yeah, so we want to meet the experiment data by the data assimilation, get the beta values, and then compute the features and do the machine learning. And then here in these gaps at angle of attack 8, and here I think 14, and higher than 18 at 19, we then make use of the trained model to spit out the approximative beta fields. And here I have to say, of course, if we wouldn't have this 0.18 here with a strong separation, we wouldn't learn the feature of strong separation. Machine learning, okay, is a nice thing, is a nice tool, but it's like in reduced order modeling, when you don't have samples which express all the physical behavior, you cannot expect a miracle that there is a forecast of a separation if your stupid network never has seen a separation. Yeah? So our network sees a separation here, and then we look how it looks like at 19 degrees. And here for the thicker airfoil, we just have the point here in between. The separation is not so strong, but we have already, due to the thickness, deviations earlier. And here you see how it looks like. So the gray box model we have, so that means the data assimilation plus the machine learning, I forgot to say, it's then a framework set up by PyTorch, and it's, as you have seen, high dimensional, so that means we use stochastic gradients and that's done by the stochastic gradient, making use of stochastic gradients in the optimizer. That's ADAM, which we also modified. Yeah? And of course, we use Tesla cards of GPU to drive this. Okay, and here you see the result. So here with the dots, this is the NACA 0012 in red without data-driven turbulence model with the standard Spalart-Almaraz. Here you have the highly separated result with a very high error, and when we do the machine learning based data-driven turbulence modeling, you see everywhere, also for the thick airfoil here, orders of error between 2 and 3%, which is the standard error. So it's nicely improved. Okay, that's the one thing. Now we come to the other side. I want to give you further messages about making use of these highly efficient, accurate adjoints, fixed point based. Here the idea is, if I have now the fixed point iterator is G, Y is the state variable, and U is the design variable, okay? Sorry for this jump in notation. So I iterate my primal solver, spits out a converged solution Y. Then I hand this over to the adjoint. So this is exactly the green way of derivation of the adjoint iterator. Yeah, and Y bar is in the adjoint community of algorithmic differentiation, the notation of the adjoint variable. So the adjoint state gets a bar, which was the lambda before, okay? So that's the iteration in the lambda before. Now it's called Y bar. And then, yeah, after you converge your primal, you get your state, you converge your adjoint, which was previously lambda. Here it's called Y bar. And this you throw in here in the design equation, yeah, which was this last equation. Yeah, you may use it directly or within preconditioner in front. If this would be the Hessian, it would be the Newton scheme for optimization, or it could be an approximate Newton, yeah. Okay, we come to it in a minute. And now the question is, instead of converging fully here, then converging there, and then converging here with the outer optimization loop, can we do this in one shot simultaneously? And the answer is yes. With the scheme we are having, we can do one update in the primal, so one update in the flow solver, one in the adjoint, making immediately use in the design update, and then continuing with an update here in the U. Yeah. So this is this framework. Yeah, here you see the Y bar is like this lambda. This is this G minus Y, yeah, which was the G minus W previously. And optimality conditions are set up that way. And if I don't converge fully, but do just one update, it looks like this. And then the question is, how shall I tune the BK that this still converges? It turns out, if I freeze the shape, if I don't modify the shape, I can simultaneously do this iteration that has been proven by the AD big shot Andreas Griewang, who was my previous supervisor on habilitation. Unfortunately, he died last year. He did a great job in doing an analysis showing when you have this contractive iterator, then your NY inherits. That was proven by me. But then in this piggyback manner, that means you put the other simulation piggyback, you can simultaneously converge the primal and the adjoint with the same convergence speed, okay? The same number of iterations. Instead of doing this separately and then this separately, you can do this together. And then you can imagine if this preconditioner in front of the design updates is in the sense of positive definiteness very big, then it's with the inverse in front very small. And if it is super big, that means this term is more or less zero, then you have this frozen shape. Then you have nothing but a piggyback update. Yeah? We know that converges. And now the trick is to make this B big enough not to violate the convergence of the piggyback and small enough to have a vast rapid improvement in design. And then it looks easy. You say, okay, I have this optimality system. I just build the derivative of a k plus 1 iterate compared to a kth iterate and evaluate it in the limit point. Then I have the Jacobian of this coupled system. And then I could analyze the spectrum there. And a sufficient condition, a necessary condition would be that this is less than 1. Yeah? And it turned out that deriving a sufficient condition on the B, which pops up here, so this preconditioner here, for this J star, which is this Jacobian, to have a spectral radius smaller than 1 has proven really difficult. That surprised us. Yeah? But that is what we needed. And the reason why this is so difficult is that this coupled stuff here somehow is driven by the Lagrangian. Yeah. By the way, that I forgot here, if I neglect this term here from the Lagrangian, then this is the shifted Lagrangian. This is why we had this notation with this NW before. Yeah. Here it's NU. Okay. It's a formality, but it shows up here in the adjoint iterator. If we augment the standard Lagrangian by the residuals in the adjoint and in the primal, which makes sense because we do this all at once and don't focus only on the design equation, but on the full coupled optimality system. Yeah, so we augment it here. And it is clear that the augmented Lagrangian, if this is fulfilling an optimality condition, it should also fulfill the standard optimality condition of this OS, this optimality system. Let's look if this is the case. Analytically, if I build the total derivative information of the augmented Lagrangian here, yeah, I can do analysis. This is really an exact thing. I have a matrix in front of this increment vector, which is just given the updates in the state, in the adjoint, and in the design. Yeah, so the increments having here, yeah, which shall be 0 at the end. So I can express the total derivative by increments with this matrix in front. And if this matrix is non-singular, it's a one-to-one mapping. And then the roots, the 0 values for the one-shot increment coincides with the roots of the augmented Lagrangian, and that is perfect fulfillment of optimality conditions. Yeah? So the first thing is we have to choose these alphas, weightings here in front of the primary residual and beta in front of the adjoint residual. Sorry, this is another beta now, of course, has nothing to do with the beta from the previous part of the talk. Yeah, so we have to choose alpha, beta, and B in such a way that this matrix is invertible. And on top, if you imagine you build a directional derivative of LA with respect to S, then it is this gradient times the normed direction S. That would be nothing but minus S transpose MS. So if this is positive definite, minus S transpose MS gives you always a positive number. Here's a minus inside. So that gives you always descent. And that means you have in each update an update which gives you descent, and that's the convergence of the one shot. Okay, and that is exactly what you do in an analysis, and we proved that. So it has to do with the determinants here and so on. I skip that part, eats up a lot of time. I'm already behind my planned schedule. However, it turns out you can find easy conditions on alpha and beta that for a B big enough, you have this property that you have descent in each step. Yeah, so it's not only positive definite, it's not only invertible, but also positive definite, and therefore yields descent. Okay, and then the question is, what means B is big enough? This is this property here, and it turns out if I build a reduced Hessian of the augmented Lagrangian, I have a lot of terms, but the last terms here are first math refugee, so are weighted by the primal and the adjoint residual, which tends to 0. So these terms can be neglected during the optimization process, and what remains here is exactly this B. Yeah, and then you see if you do one-shot optimization with this B as a preconditioner and the alpha and beta chosen in an appropriate way is nothing but a quasi-Newton method in the augmented Lagrangian problem. So the idea is we now build by algorithmic differentiation the gradient of the augmented Lagrangian and then do BFGS updates to approximate this guy. And if we have this guy approximated, it's a good approximation for the B. And let's see how good this is. You see here for an Honora M6 wing, for different numbers of surface points. Here each surface point was a design variable. On the coarsest mesh it's 18,000 degrees of freedom. You see if you double it, you have the same convergence behavior. Of course, the spurious drag, it's a drag minimization problem here for inviscid flow, reduces because you resolve physics better. But the convergence speed of an optimization compared to just a simulation is always a factor 5. So that means for the costs of 5 simulations, you are already in the optimum. You solve your optimality problem in one stroke simultaneously. Okay. And then the idea is it's mesh independent. That's no wonder, because it's close to Newton's method, as we have seen. And Newton's method is mesh independent, as one knows from numerics. Then the idea is we start on a coarse level, and then when we are in the optimum, we transfer that solution on the fine level, and then we continue. And if we do this, we have optimality for the coarse level, do an adaptation, transfer on the fine, and continue. We have a two-level, multi-level approach. It's a factor 2 in computational time. Yeah, so for 2 computations, on the fine mesh level, you are already in the optimum. Okay, and then the idea was, couldn't we now combine optimality and adaptivity? And we did also serious math investigations that it is really mesh independent and so on. Then we have a very efficient optimization scheme, and we applied it on the very efficient large aircraft configuration from DLR. You see here we have 115,000 shape variables, and we apply it for drag reduction by constant lift. You see lift is nicely kept, and the drag is reduced because we could reduce strongly the shape. Yeah? And by the way, it's very smooth, doesn't violate also the parameterization, is super local. It's the best resolution you can do because the state resolution coincides with the design resolution and a lot of nice properties. That is the fact because it's a Newton's method and it's not yielding in stupid bumps. Yeah? And also it's close to smooth gradient approaches like Sobolev smooth stuff. But I also have to skip this thing. And now, what the hell has this to do with machine learning? And now comes the joke. What we have used here in hardcore shape design, so optimization with PDE, but after the spatial discretization, it's just an ODE system in time or pseudo-time. We can make use also in standard machine learning black box applications. And you will understand this now immediately because you learned this now together with me in the aerospace context. In image recognition, it turned out it is very difficult to learn the identity. Yeah? So here we have the standard thing of network topology with input layer, output layer, hidden layers with a high amount. It's then a deep neural network. And if we have this ResNet propagation, that means we have here the identity in. So in propagation in this ResNet means identity plus something else, yeah, and that's the standard thing with weights W and biases B, and this F is the nonlinear part for nonlinear activation functions, okay? And that has been introduced by He in 2016. This kind of nets fit for image recognition, and you will see examples for image recognition at the end. They have this residual form, and that means for a given actuation here, a given nonlinear actuation function f, you just optimize these w and b, and yeah, the pairing w and b will be theta in a minute. Yeah, so you minimize over theta the output layer compared to some given data, so this loss function, as we had before. But now comes the joke. If you smuggle in this f a factor 1 over h and put a h to compensate it outwards, so this, if this is an, if this is an f tilde, so to say, and you smuggle in an 1 over h in this f, then this is the f nu, and you have an h outside, yeah? Nothing happened. So, but now comes the joke. If you reform this in that form, that reminds you to be a discretization of an ordinary differential equation. So this means a training of such a loss function with such a ResNet propagation can be interpreted to be an optimization with an ODE problem, with an ODE constraint, where the ODE is discretized in that form, which is nothing but explicit Euler. Okay? And that's very beautiful. So that means we had this black box model, but now we are back in our world, and it's even easier. It's not an ODE, it's not an PDE, it's just an ODE. However, if a student comes to me and say, oh, Nico, I'm doing this ODE constraint optimization, and by the way, I discretize the ODE with explicit Euler, I would ass kick him because it's known it's not a good idea. Yeah, you know this Euler's polygon method. Yeah, you amplify step by step the error. Yeah, but that's exactly what the machine learning guys do. If they use a standard layer topology, you as a mathematician can interpret this to be an ODE problem, ODE constraint optimization problem, where the ODE is discretized by explicit Euler, and that means layer by layer you increase errors. And then at the end you want to minimize losses. But the output layer is already error prone. So what will you do with your weights and biases to compensate this? Yeah, it's a kind of a mission impossible. So answer is, think about your topology, and that is linked to think about your discretization of your ODE. So that means, and they call it, by the way, backpropagation. They need always words for known things. So we had adjoints. So for us, the forward Euler discretization of an adjoint dynamical system is nothing but a ResNet backpropagation. Yeah? That means deep learning needs optimal control here. So you could say, I don't need to know anything about deep residual neural nets to be trained because I'm an optimization guy. I do optimal control. And everything you learn there and all the algorithmic weapons you have in your cupboard can be applied. And one was the one-shot methodology. Let's see how it works. Now comes the joke. Also, the ODE has an explicit forward time marching. There is a crazy community, the parallel in time community. They parallelize that. They have this tool XBraid, which is like an umbrella over your ODE integrator, parallelizes it, yeah, and with a high number of cores, you get an immediate gain. You can solve this with weak scaling properties, as you will see. And what we do is the forward propagation. We do with parallel multigrid, and we do this also in reverse order, yeah, with the same ansatz. So we have such a fixed point iterator now on the whole time trajectory, and we do this with some multigrid methods. and we make use of this tool XBraid. And Steffi, she was a postdoc in my group, then went to the XBraid guys, and we explained them, okay, we would like to do the derivative of your tool, and the inner derivatives we do with our Cody pack. Yeah? And the good news is XBraid is open source, you can download it, and it has the adjoint option from us. And the inner derivatives here, these phi guys here, derivatives here for the adjoint you get with algorithmic differentiation. That's a story I have seen in the aerospace context, and we do it now in the machine learning context. So that's another thing, yeah. So it's available, and then we can do a layer parallel forward propagation and a layer parallel back propagation in terms of machine learning. So it's nothing but adjoint. And then we can do a network parameter update, which is nothing but a design update. And if we do this lumpy, so that means we don't iterate, but we do this in one-shot loop, we can make use of our methodology, our one-shot methodology, exactly the same, and do one update in the complete forward trajectory as a portion of information with multigrid insight driven by this XBraid, and then one update in the back propagation. And here we do then the design updates by some Hessian approximation for this B, yeah, with several variants. I have shown you this variant I did with Andreas Kriwak and Adel Hamdi roughly 10 years ago. This is what I have shown you in the aerospace context. And then let's see how this can be applied in on image recognition. Here we have the Indian pines, so we figure out on acres here what are Indian pines, what is barley, what is whatever, or we have level set classification, and here you see how this performs for deep nets. It goes here from 256 layers up to 2,408 layers, and you see how this behaves. Yeah? It behaves nicely independent, and we have perfect weak scaling. So that means if we increase the layers together with the amount of cores, we don't have, like the standard machine learning training guys, an exploding effort. Okay, the effort is eaten up by additional cores. However, we have here perfect weak scaling, yeah, for both of the cases. So that means we have a speed up of 8 and 10. And here you see the strong scaling. So if we look into this point here, for example, so for 256 layers in 4 seconds time, we could double, no, we could, here 8 cores. We could go from 8 to double the number of cores, and then we can do in 4 seconds already 512 layers, yeah? So that's then the strong scaling here, okay? Good, and here you see how the training is. And I'm more or less in time. If I subtract my introduction. In green, this is a layer serial training, and in pink, it's with our one-shot parallel in time ODE analogy inspired optimization. It's a fraction in time, roughly a factor 10 is gained, and you see also that the accuracy of the forecast is at least as good as in the serial learning, yeah. So you have training loss in the order of 10% accuracy, which is acceptable. Thank you very much.